So today we're going to discuss the directional derivative in the gradient vector. So the directional derivative of f at p naught in the direction of the unit vector u is the real value df ds, in the direction of u at p naught. So this is going to be the limit as s goes to 0 of f of x naught plus su1, y naught plus su2 minus f of x naught comma y naught, all divided by s. Now that's of course provided it exists. And really what I want to do is I want to kind of compare this to df dx at, p naught. So if we want to look at a directional derivative, really what I'm trying to do is I can think of f of x comma y as this, this blanket function right here. So that's this shape that lives above this xy plane. So its derivative in the u direction, so the u direction being on the xy plane, kind of adding this up to show you where that point lives. We know it's going to be the slope really of this blue line, and that blue line goes in that u direction. Now this is kind of similar, well, not really kind of similar. This is very similar to, like, say, the derivative of f with respect to x. What we can tell with this is that we're holding y constant, that's not moving. I can only see that x is actually moving. So if I want to do this in that x direction, so if I only want to do this in the x direction, really my unit vector is just going to be, well, instead of like, we're using h in this case, but it's going to be h times 1, and this would be, h times 0, because we're holding this constant. So you can see that this really is just a unit vector in the x direction. So it has the exact same kind of concept as this unit vector. So really when you're looking at df dx, we're holding y constant, so we're just kind of talking about this function only in the x direction. So it would really kind of be this slope. That would be, df dx. But it turns out we can do this in any direction we want. So let me show you an example. All right, here's going to be our example. So I want to find the directional derivative of f of x comma y, which is x squared plus y. And this is going to be at that point p naught, which is going to be 1 comma 2. And this is going to be in the direction of u, which is 1 over root 2I plus 1 over root 2j. So if we recall the formula for this thing, it's going to be, it's this. So what I have to do is I have to kind of determine, it's these values here. So I know the function is going to be this. I already know what the function rule is. X naught is going to be 1, y naught is going to be 2, and then u1 and u2 are both going to be 1 over root 2. So plugging this in, I know that this is going to be the limit as s goes to 0 of f of, we'll just kind of evaluate the inside and I'll stuff it into the function next. So x naught is 1 plus, s times root 2, so s times this is going to be s over root 2, comma y naught, which is 2 plus su2, so s times this is going to also be s over root 2, minus f of 1 comma 2, all divided by s. So now we can evaluate the function at these points. So this is going to be the limit as s goes to 0 of, I know that this is your x coordinate, this is going to be your y, so it's going to be x squared plus xy. So this squared and then the multiplication of these, so x squared minus x times y, and then minus, this is going to be the evaluation of this, so x squared is going to be 1 squared plus x times y, so 1 times 2. And this is all going to be divided by s. So doing some algebra here, I'm going to square this binomial, and I'm going to multiply those two binomials. So this is going to be equal to the limit as s goes to 0. So 1 times 1 would be 1. Outside and inside is going to give us, this would be s over 2 plus s over 2, root 2, so plus 2s over root 2, plus this thing squared, so s over 2. And then I have to, actually this is a plus. I have to add, this times this. So 1 times 2 is 2. Outside is going to give us s over root 2. Inside is going to give us 2 of the exact same thing. So this is going to be plus 3s over root 2. And then plus that thing squared. So this is going to be s over root 2. And then minus, this will be 3. All over s. So we'll simplify this. What I can see is that 1 plus 2 minus 3 is going to be 0. And then we have some like terms. So I have, these are like terms. they're s over root 2's. There's 2 of these and 3 of these, so there's going to be 5s over root 2's. And this thing should have been squared, so that should be just a 2. So, so that thing squared is what goes there. So now I got these things like terms. Let me clean that up a little bit. This is over 2. So we're going to get the limit as s goes to 0 of 5s over root 2 plus s all over all over s. So we can factor an s out of this. So this is going to be the limit as s goes to 0 of factoring an s. I'm going to get 5 over root 2 plus 1. Oh, this should have been s squared. I'll get that yet. My bad. I'm trying to square this to go here. So this should be s squared. And so this would still be an s, all divided by s. So those will cancel. So this is going to be the limit as s goes to 0 of s over root 2 plus s. Sorry, 5 over root 2 plus s. I got to be careful with my 5's. When you plug in 0, this is going to be 5 over root 2. Okay, finally. So this is going to be its limit. Now what I want to show you is there's a quicker way to do this instead of doing the limit evaluation, and we can do that using the gradient and a dot product. So I'll show you that in just a second here. So what we can use is we can use the chain rule to really simplify this concept. So consider w to be equal to f of x comma y, where we are defining the intermediates as x is equal to x naught plus u1s and y is equal to y naught plus u2s. So we can really see that the independent variable is s, the intermediate variables are x and y, and then this is going to be our dependent function. So a dependent variable will be a w or f. So if I want to find dw ds or df ds, so if I want to find df ds, we know that it's going to be using the chain rule, we'll take care of the x coordinate here, and then plus take care of the y coordinate here. So this is going to be df ds times ds dx plus df dy times dy ds. So when we find these things, we'll get it. Jeez, Jeff. So cleaning that up, we know that this is df dx times dx ds, and then df dy times dy ds. So in order to clean this thing up, really what I'm trying to do is I'm trying to evaluate this essentially at our p naught. And what we can tell is that the df ds and df dy happen to be the partial derivatives of this thing with respect to x and y. And this dx ds and this dy ds, well, the derivative of this with respect to s is nothing more than u1. The derivative of this with respect to s is going to be nothing more than u2. So really what we have is this is going to be df dx. This is going to be evaluated at our p naught times u1, plus this is going to be df dy evaluated at p naught times u2. And if I let this thing be the gradient, so we consider the gradient of f to be this. It's going to be, we call this df dxi plus df dyj. Then what we can see is that this expression here is nothing more than the dot product between this gradient and then the vector u. So this ends up being the gradient of f evaluated at p naught dotted with my u vector. So again, kind of verify that this is going to be your df dx evaluated at p naught. Let's do it this way: df dxi plus df dyj. And when we dot this with your you know, your u1i plus u2j, what we can see is this times this is here, and then plus this times this is going to be here. So it is really nothing more than the dot product of these two pieces. So I'm going to erase this and kind of show you that's kind of the formulation that we have. So let's redo the previous example and then show you that's Okay, so we're going to do the exact same thing that we did before, the same function, the same initial point, and then the same unit vector. So what we know is that this is going to be the dot product of the gradient at that point dotted with, you know, your unit vector u. So first let's go ahead and find the gradient of f. So the gradient of f is going to be this df dxi plus df dyj. And this is just going to be the partial derivative. So the partial derivative of this is going to be 2x plus y. So this is 2x plus y in our I direction. And the partial derivative with respect to y is just going to be, well, that'll be 0, and this will just be x. So this is going to be xj. Now, I'm going to need the gradient of f evaluated at that point 1, 2, evaluated at p naught. So this is going to be 2 times 1 plus y is going to be 2, and this is going to be the I plus, this is just going to be 2j. So simplifying this, we have 4, 2. Making sure we have all this correct. Oh, this is x. X is 1. So this is going to be 1. All right. So now, now dotting this, we know that the directional derivative, or df ds, in the direction of u at p naught is just going to be equal to the gradient of f evaluated at p naught dotted with our unit vector u. So it's going to be this vector dotted with this vector. So we're going to multiply the x coordinates. So this is going to be 4 times 1 over root 2 plus the multiplication of the y coordinates, which is 1 times 1 over root 2. And we can see this is going to be 5 over root 2. It's the exact same value that we have. So we'll do one more example. I just really want to make sure that we know that sometimes they just give you a vector. They want to say find the derivative, and it wants in this direction, but we have to be careful that our direction must be a unit vector. So we have to write this in the unit vector. All right, here's our last example. So find the directional derivative of f of x comma y, which is 2x squared plus y squared, at the point negative 1 comma 1 in the direction of v, which is 3I minus 4j. So this example highlights the fact that a lot of times they don't give you a unit vector. So what we know is that our unit vector u is going to be equal to, you know, v over the magnitude of v. So this is going to be equal to our 3I minus 4j, all of the square root of the sum of the squares of its components. So plus negative 4 squared. So this is going to be the square root of 25, which will be 5. So this will be 3 over 5I minus 4 over 5j. Okay, so that's going to be our unit vector. So let's find that. So in order to find this, so this part of the solution, we're going to need the gradient of f. I chose a very simple function. So this is going to be df dxi plus df dyj. So the derivative of this with respect to x is going to be 4x. So this is 4xi. And the derivative with respect to y is going to be 2yj. So what I'm actually going to need is the gradient evaluated at p naught. So p naught being negative 1 comma 1. So 4 times negative 1. So 4 times negative 1i plus 2 times 1j. So this is going to be minus 4i plus 2j. All right. So that means the directional derivative is nothing more than the dot product of these two vectors. So, you know, df ds, you know, evaluated at, we'll just say it this way, at in the direction of u at p naught is going to be equal to, you know, the gradient of f evaluated at p naught dotted with my unit vector u. So this is going to be negative 4 times 3/5 plus 2 times negative 4/5. So I get minus 12 fifths, minus 12 fifths, minus 8 fifths. So this is minus 20 fifths, which is equal to negative 4. So again, what this represents is, just like derivatives, it represents essentially the slope of the tangent line. Well, this is the slope of the tangent line that moves in the direction of u.